This is a special kind of a compound where you have all the carbons in a ring or a loop, and you have alternating double single bonds. Now, at first, this might look like a cycloalkane, but it's more than that because you have double single bonds. It might also look like an alkene with double bonds, but we're going to see that this is a whole nother group altogether. So what this is an example of is what's called an aromatic hydrocarbon. An aromatic compound is when you have double bonds that can resonate. They move literally from left and right around the track. Now notice that this is a flat structure. All right, all of the double bonds are above and below this 6-ring structure, and they do literally move around. They resonate around. So sometimes what people will do is they'll draw that circle in the middle right there. That's the fact that represents how these kind of compounds, that resonance makes the double bonds go round and around and around and around. So aromatic compounds are amazing. They're almost like science fiction to me. It's so weird. They're flat because those double bonds that resonate go back and forth, and they're very, very stable. And there's actually a whole bunch of these aromatic compounds, but I want to focus here on benzene, which is the simplest of the aromatic compounds. Benzene gets the formula C6H6, and that's what we see rotating right there. Again, benzene is amazing. It's not quite an alkene. It's not like a cycloalkane. It's a whole other kind of compound, and it has a completely different reactivity to it. Benzene is pretty amazing. These are 3 different views of benzene. The upper left one is what we call the sigma network. Those are the single bonds that connect the carbons to the carbons to the hydrogens, all that kind of jazz. But check out the lower left-hand one. That's the pi network. And you can see it's like 2 donuts, if you will, like one on top of the other. All those pi bonds, those double bonds and the pi bonds, they're resonating, all right? They're delocalized. They're not just between 2 atoms. They're actually connected to all 6 atoms. So it creates, if you will, like a force field above and below the sigma network. So when you put them all together in the upper right, that shows the sigma and the pi bonds. It's amazing, all right? Delocalized just means that instead of having double bond between 2 atoms, the double bonds literally resonate around the molecule. It's like a racetrack. And again, I said shields around the sigma network. That's not too bad of an explanation. And that's why these things have their own like reactivity. They're totally cool compounds. In a normal compound, a carbon-carbon single bond, about 154 picometers, and a carbon-carbon double bond, roughly 134 picometers. Well, in benzene, you have 139 picometers. So notice it's certainly not single bond length. It's a lot shorter, but it's not quite double bond length. And we talked briefly earlier how as bond order goes up, the bond length goes down. So that's why a bond order 2 double bond is shorter than a bond order single bond. So 134 is shorter than 154. Well, carbon-carbon bonds in benzene aren't doubles or singles. It's more like 1.5. It's kind of in the middle. And you can see it's actually close to a double bond. This is a very stable molecule. So instead of being a single or a double, we would say the CC bond order in benzene is 1.5. But it's probably closer to 2. This is so stabilized because of those pi electrons that are kind of floating like donuts around the molecule. Benzene's amazing. You'll talk a lot more about this in organic chemistry, but I just wanted you to hear this and kind of hear these terms so that you'll be good to go and be able to figure it out. You can put pieces on the benzene molecule, and these are just different examples of them. Probably the most famous of all of these is this one right here. The official name is methyl benzene. It's a methyl group off the benzene ring, but people call it toluene. You can buy toluene at Fred Meyer's. It can be used as a paint solvent, all kinds of different things. All these other names are maybe things you've heard of before. Nitrobenzene. Nitro is an NO2 group. Benzoic acid is actually a COOH. We'll talk about that a little bit. Once in a while you hear about phenol. I was listening to a movie the other night and they actually said phenol a couple times. I was like, Anyway, phenol is an OH group of the benzene. And you can also put the benzene groups together. And that's what this naphthalene thing is. It's like 2 benzene rings kind of fused together. And you can have halogens, bromobenzene. You can have alkyl groups off benzene, ethylbenzene. lots and lots and lots of possibilities. If you have species on the benzene ring that are the same, you end up with another kind of nomenclature I want to introduce. In the old days, they called them ortho, meta, and para. And ortho means that the two groups that are the same are right next to each other, like 1 and 2. Now on benzene, you have a total of 1, 2, 3, 4, 5, 6 places they can go. So if the two similar pieces are next to each other, like 2 chlorines or 2 bromines or 2 methyl groups, whatever, then that's called ortho or just O dichlorobenzene. But I would prefer that you use numbers for it so no one's confused. 1, 2 dichlorobenzene would be an alternate way, but you will see ortho used a lot or ortho dichlorobenzene. Either one is fine. Now, if the species are there's like a carbon between them, like that carbon's between this one and this one, then it would be a 1,3-dichlorobenzene, but people will call it meta-dichlorobenzene or just M-dichlorobenzene. And finally, para means 1, 4. They're literally 2 spots away. 1, 4 would be 1,4-dichlorobenzene in this case, or para-dichlorobenzene. Now, if you're thinking, why isn't there a 1,5-dichlorobenzene? There absolutely could be, but if you think about it and you number instead of left, like going clockwise, if you go counterclockwise, you'll see that 1,5 would be actually the same as 1,3-dichlorobenzene. So again, you can number these things in both ways. I'm talking about them here in clockwise fashion, but you should think about what they would be in a counterclockwise fashion as well.